So now in the earlier lecture we had got an understanding of the physical mechanism of which you reach the upper critical field. That is when the normal cores start overlapping and the superconducting fraction is almost lost, because you have everywhere normal cores which are reaching very close to each other. That is the point you reach the upper critical field. Now let us try and do a calculation for the upper critical field. How does one actually calculate the upper critical field? And for that we start with the first GL equation, namely 1 by 2 m star h cross by I del plus 2 EA, the vector potential, the whole square psi, plus alpha psi plus beta mod of psi square psi is equal to 0, where m star, if you recall, is twice of m. We had actually, if you go back to the earlier lecture, this is written as 4m, but you can also write it as 2m star. It's somewhat easier to do that. And this is of course the Cooper pair charge of 2e. So this is the first Ginzburg-Landau equation. Now what we do is that we will consider that the magnetic field B that we apply is H times Z cap. Namely, we are applying a magnetic field in the Z direction, and we can write, because we are applying a magnetic field in the Z direction, you can write the vector potential Hx y cap. This is easy to show if you consider that curl of A is equal to B. So if B is this, you can show that if you put this expression into here, you will get this, exactly this out, okay, by using this curl of in the rectangular coordinates. You can just do that. And also this value of A satisfies divergence of A is equal to 0, the London's gauge. Okay, so both these equations are satisfied. This is the London's gauge of a superconductor, since we are working in the London's gauge. So basically you will have to use this form of the vector potential when you put it in. So therefore 1 by 2 m star will be H cross by I del plus 2 EX H y cap square psi plus alpha psi plus beta mod psi square psi is equal to 0. Okay, and you can therefore simplify this further. Okay, you can open out the brackets. Y cap dot del cap will give you, of course, del by del y. Okay, you will get this sort of a term. So if you simplify this, opening out the bracket, you will get minus h cross square by 2m star del square plus h cross by I 2e h x by m star del by del y plus 2exh the whole square by 2m star into psi plus alpha psi plus beta mod psi square psi is equal to 0. So we can now, this term, let us define omega c as 2EH by m star, which is nothing else but the cyclotron frequency of a Cooper pair in a magnetic field. Okay, because this is nothing else but 2EH over twice of M, and this is nothing else but EH over M. Okay, you can also write this as a charge E star, where E star, this is nothing else but the charge E star, where E star is twice of E, which is the charge of a Cooper pair. So omega c is essentially the cyclotron frequency of a Cooper pair. Okay, so then the above equation that we have obtained here can be simplified to minus h cross square by 2m star del square minus I h cross omega c x del by del y plus half m star omega c square x square psi is equal to minus alpha psi minus beta mod psi square psi. Now, this is where we do the first thing. Now for H going to HC2, normal cores will overlap and the superconducting fraction will go to 0. Therefore, mod of psi square will tend to 0. As this happens, so therefore for H tending to HC, this term will tend to 0. This term that we have here will tend to 0 in comparison to minus alpha. So beta mod of psi square psi will be much less than alpha psi, because since mod of psi square will tend to 0 as your normal cores will start overlapping, so because of the superconducting condensate fraction will be almost negligible, and therefore the above equation is almost like a Schrodinger's equation, h cross square by 2m star del square minus I h cross omega c x del by del y plus half m star omega c the whole square x square psi is equal to minus alpha psi. This is nothing else but a Schrodinger's equation. This is like a Schrodinger's equation with eigenvalue minus alpha. Okay, with an eigenvalue minus alpha. You have also solved this equation earlier in quantum mechanics, where you have looked at a particle in a magnetic field and you have solved for the Schrodinger's equation, and you have landed up with exactly the same type of an equation. Okay, for a particle in a magnetic field, and this can be mapped to a shifted harmonic oscillator. You can easily show that this is like a shifted harmonic oscillator. But to solve this, let's go on a little. I'll show you that you can use an ansatz. You can use an ansatz that psi xy is e raised to I kyy f of x. One has a potential basically only in the x direction, so the particle is there is a potential only in x direction, and the particle is free in y direction. So therefore you have a plane wave like solution along the y direction, and you are using a function along the x direction, because there will be some sort of confinement in the potential in the x direction. So you can use this ansatz and you can put it back here, and when you do that and you can work it out, you can show that this is equal to minus h cross square by 2m star d square f by dx square plus half m star omega c the whole square x square plus 2 h cross ky by m star omega cx plus h cross square ky square by m star square omega c the whole square times f is equal to minus alpha times f. Okay, you just have to put that back, do a little bit of calculation, and you can easily show this. Now if you take x naught is equal to minus h cross ky by m star omega c, then the above equation reduces to minus h cross square by 2m star d square f by dx square plus half m star omega c the whole square x minus x naught the whole square f is equal to minus alpha times f. This above is the Schrodinger's equation for a particle in a harmonic potential whose origin is shifted by x naught. This is something that you have done in quantum mechanics, and we also see the similar thing happening from the Ginzburg-Landau equation. You have the same expression which comes up into this picture. So now the solution alpha is very easy. The solution minus alpha is basically your the eigenvalues of the above equation. The eigenvalue En is equal to n plus half h cross omega c. Now for a superconductor, the ground state is n is equal to 0. Okay, so the eigenvalue E for n is equal to 0 is half h cross omega c, which is minus alpha. Okay, that is the lowest energy state that you are considering. Okay, so therefore minus alpha will be equal to h cross by 2 omega c, which is equal to h cross E bc2. Omega c is E bc2 by m for h equal to hc2. Okay, if you are considering h equal to hc2 or b equal to bc2, then this is equal to, so that is where we are substituting this here, and this is m 2m, or that xi square would be h cross square by 4m minus alpha. Remember that minus alpha is a t minus tc for t less than tc. This was okay, and this is xi square, and so you can rewrite this expression for minus alpha as h cross square by 4m xi square, which is h cross E bc2 by m, and therefore bc2 becomes equal to h cross by 2e xi square, which is h by 2e into 1 by 2 pi xi square, or your upper critical field bc2. This, if you recall, is nothing else but the flux quantum phi naught. So this is the flux quantum phi naught 2 pi xi square. This is your calculation of your upper critical field of a superconductor. Upper critical field of a superconductor. And so that is what we will discuss in the next lecture.